Hello student, welcome to Math Solution Academy. Now I show you that how to determine the subspace of a vector space. Now I hit a problem. The problem is which of the following is the subspace of the vector space R3. First of all, what is subspace? If if V is a vector space and W be a non-empty subset of V such that a vector say alpha belongs to W and beta belongs to W, this imply alpha plus beta belongs to W and a scalar A belongs to F, where V is a vector space over F and alpha belongs to W, this imply A alpha belongs to W. If the two conditions are held for a non-empty subset W of a vector space, then W is called a subspace of the vector space V. Now, if we combine these two conditions, we get another condition A alpha plus B beta belongs to W, where alpha beta belongs to W and AB belongs to the scalar F. If this condition is held, then we also called W is a vector space. If any of these, if this or this condition became hold for a non-empty subset W, then we say that this is a vector space. This is a subspace of the vector space V. Now we look at the problem. The problem is which of the following is a subspace of R3. The first is x, y, z belongs to R3 such that x plus 2y equal to 0 and 2x plus 3z equal to 0 be a set. Now let alpha equal to x1, y1, z1 be a vector. We say it W and beta equal to x2, y2, z2 belongs to W. So and A be a scalar since this is a vector space over R is a real number. So alpha plus beta equal to x1 plus x2, y1 plus y2, z1 plus z2. We use addition of two component in vector space, and since this belongs to W, so the condition is 2x1 plus 3z1 equal to W, 2x2 plus 3z2 equal to W, x1 plus 2y1 equal to 0 0 and x2 plus 2y2 equal to 0. Now we see this 2 of x1 plus x2 plus 3 of z1 plus z2, and we see that 2x1 3z1 and 2x2 3z2, and this is generally W 0 at x1 x2 plus 2 of y1 y2, and this is also 0 from this. And if we multiply a scalar A into A alpha equal to A x1, A y1 and A z1, and this is also hold. the condition, because 2a x1 plus 3a z1 equal to 2x1 3 z1, and these hold the another condition. So therefore A is a subspace. Now we check the second condition. The second condition here W equal to 2x 3y 4z equal to 3 and z equal to 0. Now you see that the null vector 0 0 0 not belongs to W, since it does not satisfy the condition this, because 2 into 0 plus 3 into 0 plus 4 into 0 not equal to 3. So W is not a subspace of the vector space R3. So this is wrong. Now we check the third condition. The third condition is x, y, z, W3, say it W3, and such that x greater than equal to 0, y greater than equal to 0. Let alpha be x1, y1, z1 belongs to W3, and we take a real number R such that A is negative. So what is A alpha? A alpha equal to ax1, ay1, az1, and you see that ax1 less than 0, since x1 greater than equal to 0. So ax1 less than equal to 0, and also ay1 less than equal to 0, since y1 greater than equal to 0. So therefore A alpha not belongs to W. So the condition C is also false. Now we check the fourth condition. The fourth condition is W4 equal to such that x minus 1 equal to 0 and y equal to 0. This is similar to the second option. 0 0 0 not belongs to W4, since 0 minus 1 not equal to 0. So W4 is not a subspace of R3. So the option D is also false. So the right option is A, and the options B, C, D are false. Now the second problem is, let V be the set of 2 cross 2 matrix A11, A12, A21, A22 with complex entities such that A11 plus A22 equal to 0. That means trace of the matrix is 0. And let W be the set of matrix in V with A12 plus A21 bar equal to 0. Then under the usual matrix addition and scalar multiplication, which of the following are true? The first option is, let V be a vector space over R. Now V is a vector space. Now V is this type of vector space belongs to M2R such that A11, A22 equal to 0. That means trace of the matrix is equal to 0. Now we check that it is vector space over C or not. Let alpha be a matrix A11, A12, A21, A22, and beta be another matrix B11, B12, B21, B22, and both belong to V. Then A11 plus a22 equal to 0 and b11 plus b22 equal to 0. And let a and b be two scalar. Then a alpha plus b beta equal to a11 a12 a21 a22 plus b into b11 b12 b21 b into b22, and this became a into a11 b11 a12 bb12 a21 b b b b21 a22 plus b b22. Now I check that the diagonal of this is 0 or not. Now the diagonal is b into b11 plus a into a12 plus b into b1 a into a22 and b into b22, and this became a11 plus a22 and b equal to b11 b22, and that means a into 0 plus b into 0, so this became 0. So we see that this is a vector space over C. Since a alpha plus b beta belongs to V for all alpha beta belongs to V, and sorry, I changed my pen because the ink is finished. So this beta 1 belongs to V. For all, this sign is called for all, alpha beta belongs to V, and for all AB belongs to C. So the option V is a vector space over C is right option, and V is a vector space over R is also right, since real number is subset of complex numbers. So since V is a vector, since a real number is subset of complex number and V is a vector space over C, so V must be vector space over R, and this is always true because the extension of the field is C. C is a field extension of real number. Now we check the vector space W. The set W. The set W equal to A11, A12, A21, A22 belongs to M2R, such that A12 plus A22 1 bar equal to 0 and A11 A22 equal to 0, because the question is W is a set in V. So here I only check that this is not necessary because W is a subset of V and every element of V satisfied this, so W must satisfy this condition. Now we only check this condition. Let alpha equal to, here alpha A11, alpha A12, alpha 21, alpha 22, and beta equal to B11, B21, B12, B21, and B22. And in the previous case, we see that B beta equal to A11 A12 sorry A11 B11 A11 B into B11 A into A12 plus B into B12 A into A21 plus B into B21 A into A22 plus B into B22. I see that from the previous case. Now the condition is the conjugate. Now the condition is this plus conjugate of this. So this became A A11 plus B11 plus of A22 plus B2 sorry extremely sorry A12 B12 plus A21 BB21 this conjugate, and this became A12 plus BB12 plus A bar A conjugate A21 conjugate plus B conjugate B21. Now if A and B are chosen from the real vector field, then A conjugate and B conjugate is equal to A and B. So A12 plus BB21 plus A into A21 plus B into B21. This is bar, and A equal to A12 A21 bar plus B into B12 plus B21 bar, and naturally A into 0 into B into 0 equal to 0. Since these two matrix belongs to W, so by the given condition of W, so by the given condition of the A12 plus A21 bar, A12 plus A21 bar equal to 0. So A12 plus A21 bar plus B12 plus B21 bar equal to 0 if for all AB belongs to the real field. So W is a vector space over C is true. Now we check W is a vector space over C is true or not. If AB belongs to complex vector field, then A not equal to A bar and B not equal to B bar. So we here take a counter example. If B equal to 0, and first of all if we take a matrix A equal to, if you take a matrix A equal to alpha equal to 1 I minus I, then you see that I plus I bar equal to 0. So alpha belongs to W, and beta is another arbitrary matrix A B C D, where B plus C bar equal to 0. So beta belongs to W. Now we take A equal to I and B equal to 0. Then A alpha plus B beta equal to I into 1 I minus I to 0. This became I minus 1 minus I, and you see that minus 1 plus of minus 1 bar equal to minus 2, not equal to 0. So in that case A alpha plus B beta not belongs to W. Whenever alpha beta belongs to W and AB belongs to C, but this not belongs to W. So W is not a vector space over the vector field C. So W is not a vector space over C. So the option B is a wrong option. Thank you.